All right, let's dive into something pretty wild. We're talking about the strange physics of supermaterials, these incredible substances that are strong enough to build jet engines, but can sometimes shatter in the blink of an eye. So what's going on here?
Here's the central puzzle, right? It's this crazy paradox. We build our most advanced, most critical machines. We're talking rockets, race cars, you name it, out of these materials because we think of them as being unbelievably tough. But here's the secret. Strength isn't some fixed, static number. It's a moving target. And the one thing that changes it all isn't just how hard you hit it, but how fast.
And that idea brings us right to our first section, the speed-strength paradox. This is where all of our normal intuitions about how things work kind of get thrown out the window. It's really cool stuff.
Okay, so the core scientific reason for all this has a pretty technical name, strain rate sensitivity. I know it sounds a little intimidating, but the idea behind it is actually super simple. It just means that a material's properties can completely change depending on the speed of an impact. It's the hidden variable that engineers are totally obsessed with for a very good reason.
This slide breaks it down perfectly. On one side, you've got a low strain rate. Think of it as a slow, steady push, like when you bend a metal spoon. The metal has enough time for its internal structure to shift, to move, to deform. But a high strain rate, whoa, that's a whole different ballgame. That's a blast wave, a sudden collision. The force hits so fast the material has zero time to adjust. So instead of bending, it just breaks. Speed really does change everything.
So, what kinds of materials are we actually talking about here? Let's meet some of the stars of this high-speed drama. First up, you've got nickel-based superalloys, things like Inconel 625. This is the heavy-duty stuff you find in the heart of a jet engine or a rocket nozzle. For these guys, it's a double whammy of speed and intense heat. At incredibly high temperatures, their atomic structure actually changes and softens up, so a sudden shock can cause them to fail in ways they just laugh off when they're cool. And, that's a detail you really care about when you're hurtling through the sky. Next up, carbon fiber reinforced polymers, or CFRPs. You know the stuff from Formula One cars and the newest aircraft. Everyone loves it because it's insanely strong and ridiculously lightweight. But when it gets hit hard and fast, its survival depends on how thousands of tiny internal fibers work together. If the impact is just too fast, those fibers start to snap before they can pass the load along, kicking off this microscopic, unstoppable chain reaction of failure. Okay, now this is where the science gets, well, kind of mind-bending. Titanium alloys, absolutely essential for the aerospace industry, can do something that sounds like it's straight out of science fiction. When you hit them hard enough and fast enough, their internal crystal structure can instantaneously transform. It's called a phase transformation. For just a microsecond, the material literally becomes a different substance with totally different properties. How wild is that? And it's not just these exotic, high-tech metals and composites. Even something like concrete can be a supermaterial. We're talking about ultra-high-performance fiber-reinforced concrete, which is designed for things like protective bunkers. Its entire job is to absorb a blast without failing, and its ability to do that is 100% dependent on its strain rate sensitivity. It's all about how its internal structure reacts to that sudden, immense pressure.
So, what does one of these failures actually look like up close? Let's zoom way in and look at the anatomy of a high-speed break to see what's happening deep inside the material.
Right. You have to forget everything you can see with your own eyes. We are talking about an invisible, high-speed ballet of physics that unfolds in millionths of a second. A shockwave tears through the material, heat flashes into existence, and this whole cascade of failures just begins. Let's use that carbon fiber we talked about as our example. Okay, step 1, the shockwave hits. A pulse of pure energy just rips through it. Step 2, individual fibers which have no time to stretch just start snapping. Step 3, the bonded layers of the composite begin to peel apart from each other. That's a process called delamination. And step 4, well, all of this damage cascades almost instantly, leading to catastrophic failure of the whole thing. Now, as you can probably guess, trying to study, let alone predict, these incredibly fast, microscopic events is a massive challenge. And this brings us right to the unseen frontier of materials science. This slide really nails the big problem scientists are still trying to solve. First, you've got microstructural blind spots. Basically, we can't see the exact atomic level flaw where a tiny crack first begins. Then there's measuring real-time heat.
The flash of intense heat generated by an impact is so fast it's almost impossible to capture what's happening as it happens. And finally, these coupled degradation mechanisms. That's just a fancy way of saying we don't fully get how the heat and the force of the impact team up to weaken the material.
And that's really the bottom line, isn't it? This quote says it all. If we ever want to design the next generation of materials that are truly resilient, we have to bridge these gaps in our knowledge. We have to find a way to see the unseen. Which brings us to our final section and the big so what question. Why does all this microscopic, crazy fast science matter in the real world? Well, it matters because we are constantly engineering for extremes. Understanding this science is exactly how we design cars and planes that are both lighter and safer in a crash. It's how we develop better body armor that can stop high-velocity threats. It's how we build structures that can actually withstand an earthquake or an explosion. Seriously, every single leap forward in these fields depends on getting this fundamental physics right. And just to put all of this into perspective, think about this number: 1/1,000,000th of a second. A single microsecond. That's the timescale we're working on. The entire story of whether a critical component survives or fails can be decided in that tiny, imperceptible slice of time. Designing for that world, it's one of the greatest challenges in all of engineering.
So in the end, it all comes back to this one big question. From the engines on a starship to the armor protecting a soldier, our technological progress is tied to understanding materials at their most vulnerable moment. By decoding the secrets of these high-speed brakes, we aren't just making stronger stuff, we are literally paving the way for technologies we can only dream about today.